here, I am visiting a bamboo forest in Japan. In Tampa. Tampa, Florida, the United States. So in particular, what I want to talk to you about today are control systems, and really nonlinear control affine systems in particular. And so why don't we go ahead and talk about nonlinear control affine systems and dynamic mode decompositions for them. And, well, this will be a fun lecture. Now that I've had 2 doses of the Pfizer vaccine as of a week ago, I felt it was time to do some traveling. Outside, because it hasn't been 2 weeks yet. At the same time, the Tim Traveler posted a challenge that he called
the International Staycation Challenge. Your mission is to find somewhere near you that looks like it isn't. In other words, go somewhere in your local area, in your country, that looks like it's from another country. It can be an unusual building, monument, landscape, anything that makes it look like you're in a different country to the one you're really in.
The idea was to go to a place in your local area that looks like it isn't. Possibly, with a little movie magic, you can make it look convincing that you are somewhere else. If you're in Florida and you really want to dive into this sort of thing, then a visit to a place like St. Augustine, which is a very European-looking city and the oldest city in the United States, would pretty much accomplish exactly what you're after. And possibly another place to visit would be, say, Mount Dora, which is another nice option where you can find a genuine German restaurant. But these are both a bit out of the way when you're traveling with 2 toddlers. So I thought I'd go visit a botanical gardens maintained by the university I'm a professor at, the University of South Florida. The USF Botanical Gardens have all sorts of incredible exhibits and activities, including carnivorous plants, yoga in the garden, a beekeeping class, and seasonal festivals. But of course, we aren't here to see any of that. If you know anything about Florida, then you know if you go hiking outdoors, you are likely to run into the last remaining dinosaurs, extremely venomous snakes, huge spiders, and, well, a lot of mosquitoes. And this is very much not anything like what I'm trying to show you now. What I was looking for was an artificial, quote, Japanese bamboo forest. And, well, here it is. Now, ultimately, it was a little bit disappointing. You see, this is, well, all of it. This isn't the biggest botanical gardens in the area, but if I frame the shot well enough, perhaps it looks convincing? If I really wanted to make this convincing, then I should have traveled a couple hours north to Gainesville, Florida, where the Kanabahal Botanical Gardens has a much larger presentation, but for little gardens here at the University of South Florida, this isn't all that bad. So, this video is really about doing some data-driven methods for control affine systems. And you might be wondering, what does all this staycation and traveling have to do with control affine systems at all? Well, the whole reason why we are in a quarantine is because you, me, and the rest of the world has been involved in probably the largest control effort for controlling a control affine system.
Hey. Daddy.
Hey, boy.
Hi.
And this can be seen through the SIR model, which models disease spread and infections. And in particular, if you frame this in just the right way, and you move over a couple terms out of, say, the susceptible differential equation and the infected differential equation, and you move them to the side, then there's this extra parameter that's on there, this, say, sigma. And that sigma represents what proportion of the total number of interactions, S times I, that can happen between pairs of people throughout the world. It tells us what proportion of those ends up having a transmission from an infected person to a susceptible person. And the whole idea is that we want to make that parameter very, 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 very small. And that's what the quarantine does. It reduces the total number of interactions, and therefore we can see it flattens the curve. And so everybody you know has been involved in some control affine setup, at some point in the past couple years. And so now here what we're going to be talking about is, well, more control affine problems, and given an unknown control affine dynamical system, how we can do, say, something like data-driven methods in order to do some modeling, some prediction, and, well, how to do dynamic mode decomposition for control affine systems. So Stick in here and let's go ahead and start talking about it. Up to this point, if you've been following my lectures, then thus far we've only covered autonomous dynamical systems. These are dynamical systems that will run without any sort of intervention from you or me. This includes classical topics like celestial mechanics, where the orbit of a planet does not really care if you, say, jump on it or hit it with a big rock. And of course, it includes a lot of other systems that we intend to run without any sort of input. Now, when we had an unknown autonomous dynamical system, what we did is we took a whole bunch of trajectories that we observed from the dynamical system itself, and we embedded these trajectories into a Hilbert space through something we called occupation kernels. Occupation kernels embed this trajectory as a function, and this function is represented as, say, the integral from 0 to t of k of x, comma, the trajectory evaluated at t, integrated dt. And these functions sit inside of this reproducing kernel Hilbert space, and they have a special operator that they interact with called the Liouville operator. The Liouville operator's adjoint, when it hits the occupation kernel, that corresponds to a trajectory that itself corresponds to the dynamical system that the Liouville operator represents. It will actually give us a difference of two kernels, each of which are centered at the two endpoints of our trajectories. And this allows us to get a sample of our Liouville operator using only the data that we observed. And so what we did then is we found a finite rank representation using this sample, and it's allowed us to do a sort of spectral decomposition of the finite rank representation, which we hope is close to the original Liouville operator. And then it gave us eigenfunctions, and then we projected the full state observable onto these eigenfunctions, and that allowed us to construct a model for our system state. Today we are shifting focus, and we're going to be considering dynamical systems that take inputs. This includes things like the SIR model that we just discussed, your thermostat, and even video games. However, these systems are so varied that we're going to have to restrict ourselves to a very particular class of these systems, and today we're going to be talking about control affine systems. So a control affine system takes this following form. It's going to be x dot is equal to f of x plus g of x times u. F of x is something we call the drift dynamics, g of x is the control effectiveness matrix at x, and u is a function of t that is called the control input. And the special case where u of t can be written as another function, say mu, evaluated at x of t, we call this a state feedback controller. And the state feedback controller does something that we call closing the loop. And when you use a state feedback controller, you ultimately get an autonomous system at the end of the day. And for this autonomous system, we can try to appeal to our analysis that we just talked about using these Liouville operators and the occupation kernels. And in fact, we're going to do something very close to that.
To say hi! You have to say hi to mosquitoes. They're pretty cool.
So from this data-driven perspective, we're going to assume that we do not know f and we do not know g. We have a collection of controllers that we've observed, and we observed not only the controller, but the control trajectory. And in the data-driven context, we have a feedback controller that we're trying to analyze using the data that we've observed from the system. And so we can go ahead and make occupation kernels corresponding to the control trajectories, and we can basically look at the Liouville operator compressed to the span of these. And so we're looking at the restriction of this Liouville operator to the span of these occupation kernels. Then we're going to hit that Liouville operator with a projection on the other side, and this projection will project back onto the span of these occupation kernels. The reason why we do this is because we want to be able to find a collection of eigenfunctions for this finite rank representation that is expressible solely through these occupation kernels. And our intuition says that if we have enough of these occupation kernels to the point where the span is dense inside of our space, and then that should give us a very close approximation to the actual Liouville operator that we really care about. And this is, of course, modulo any sort of convergence theorems or guarantees. And so right now this is just strictly a heuristic, but later on I'll tell you how we can make this a lot more solid. However, you'll notice that there's an immediate problem with this. Each of these occupation kernels correspond to a control trajectory that it corresponds itself to a very particular controller. Each time you change the controller, you are technically changing the dynamics. So if you are trying to analyze the Liouville operator that corresponds to the closed loop that we obtained, by using the state feedback controller, then the issue is that when you hit the adjoint of that onto these occupation kernels, you're not actually going to be able to exploit that whole difference of kernels feature, because that occupation kernel trajectory corresponded to the dynamics are obtained through a different controller. So we're going to have to do something a little different, and we're going to have to split up this operator, this Liouville operator, into two different operators. And when we do that, we're going to actually have to insert something in the middle where we're going to use something called control occupation kernels. These control occupation kernels are going to interact with those two pieces of operators, and it's going to allow us to make a finite rank representation. So why don't we go ahead and talk about what these operators actually are. So why don't we go ahead and take a look at our Liouville operator applied to an observable from our reproduced kernel Hilbert space. What this Liouville operator does is that it takes this observable and it sends it to the gradient of h times f plus g times mu, where f plus g times mu is the autonomous dynamical system that we got from the state feedback controller. Now, what I'm going to do here is I'm going to factor that right-hand term. And so I'm going to go ahead and rewrite it as this matrix that in the first column has the drift dynamics, and the rest of the matrix is our control effectiveness matrix. Now on the left-hand side, this is multiplied by the gradient of h, that hasn't changed. And on the right-hand side, I'm multiplying it by this column vector, 1 and mu. And so this is going to give us two different operators. One, which we're calling the control Liouville operator, is going to be given by the gradient of h times that matrix. And if we take a look at it, the gradient of h is an n-dimensional row vector, and this matrix has n rows and m plus 1 columns. So the ultimate result of this multiplication gives us an m plus 1 dimensional row vector, where m is the dimensionality of our controller. Now the other operator is a multiplication operator, and it is going to be taking our vector valued functions, our m plus 1 dimensional row vectors that we would get out of the Liouville operator, and it is going to multiply them on the right hand side by this column 1 mu. Now 1 mu is going to be an m plus 1 column vector because, well, our controllers are m dimensional. So ultimately, this multiplication ends up giving us a scalar valued function. So at the end of the day, we have our control Liouville operator, which is going to give us a vector valued function, and this vector valued function is going to be sent back to scalar valued functions by the multiplication operator. But this does require us to introduce a new notion, and this is called a vector valued reproduced kernel Hilbert space. When I say new, I mean it's mostly new for this class. We did talk about it briefly when we discussed dynamic mode decompositions for higher order dynamical systems, but this approach is a lot less complicated. So why don't we go ahead and jump into what a vector valued reproduced kernel Hilbert space actually is. And in doing so, we're going to introduce a new kind of occupation kernel called the control occupation kernel. And this is going to allow us to embed not only our trajectory information, but also the controllers that go along with them. Vector valued reproduced kernel Hilbert space. It is a Hilbert space of functions that are going from some x, and this x is usually Rn. These functions map x to a Hilbert space of some kind, and this Hilbert space we're going to call y. And in our case, this Hilbert space corresponds to r to the m plus 1 row vectors. Now, in order to make it a reproducing kernel Hilbert space, we're going to need a collection of bounded functionals. And in fact, what we're saying is that for every x in x and v in y, the mapping that takes h to h of x inner producted with v with respect to the y inner product, that has to be bounded. And if that is bounded, the Riesz representation theorem tells us that there is some special, say, kernel function k sub x comma y, such that h inner producted with this special function, this special kernel, ends up giving us the other inner product. Now, it turns out that this mapping that sends v to k sub x comma v is actually a linear mapping, so we can go ahead and rewrite this as k sub x acting on v, where k sub x is an operator that takes you from the Hilbert space y to the Hilbert space h. And we have something we call the kernel operator corresponding to the reproduced kernel Hilbert space, or the vector valued reproduced kernel Hilbert space. And this is given as kxy is equal to k sub y star acting on k sub x. And in the case when y is equal to r to the m plus 1, this kernel operator is simply a matrix. And in our case, when it comes to computations, we're really just going to take this to be the diagonal operator, where we have a kernel function along the diagonal. And this is going to make computations for us really easy. And honestly, since we're choosing these kernel functions ourselves, unless we know more about the dynamical system, there's really very few other options that we can choose in any sort of considered way. We're going to make something like an occupation kernel, and this one's going to correspond to two different signals. One is purportedly our control signal, and the other one is a signal from our trajectory. And so what we're going to do is we're going to start with two signals, and these signals are going to be theta and psi. Theta maps us from 0 to t to r to the n, and psi maps us from 0 to t to r to the m, where m is the dimensionality of our controllers, and n is the dimensionality of our space. So now we're going to take a look at the functional that maps us from p, our row-valued function, and we're going to take a look at the mapping from this p to the integral from 0 to t of p of theta of t times 1 and psi of t. And now this is integrated dt. Now, if you rearrange your terms just right, you can see this is going to be equal to the integral from 0 to t of p interproducted with the kernel function corresponding to theta of t comma 1 psi of t. And this is an inner product in our Hilbert space, and this is integrated dt. So then we can use the Cauchy-Schwarz inequality, and we can show that the absolute value of this integral is going to be less than or equal to the norm of p inside of our Hilbert space times the integral from 0 to t of the norm of k sub theta of t comma 1 psi of t, and this integrated dt. And with a little bit of continuity assumptions on rk, we are then guaranteed that this is going to be a bounded linear functional. And since it's a bounded linear functional, that means that there is going to be some special function which we are calling our control occupation kernel that corresponds to each of these signals, the theta and psi. And this is inside of our Hilbert space. And what happens when you take an inner product of p with this occupation kernel is that you end up getting this integral back. And these are our new occupation kernels, and we call them control occupation kernels because they interact really nicely with this control Liouville operator when you have psi as being the controller that gives you the control trajectory theta. And generally speaking, I'm going to refer to the control trajectory as gamma sub u and our controllers as u. So what we're going to have is we're going to have a whole bunch of different projections that are going to be happening around these two different operators. And in particular, what we're going to do is we're going to take one of these occupation kernels that corresponds to our control trajectories, and we're going to be looking at its image underneath this control Liouville operator. And then we're going to take that image and we're going to project it onto the span of these control occupation kernels that correspond to these controllers and these control trajectories. So we need to figure out what that projection looks like. Now, just like with any projection, we need a gram matrix of the bases that we're projecting onto. So we're going to need a gram matrix for our control occupation kernels. That's easy enough. It's written like this. And what we're going to be doing is we're going to be looking at the inverse of this gram matrix applied to a vector of the occupation kernel's image underneath the control Liouville operator. And we're going to have a column of that image interproducted against each one of these control occupation kernels. And so in order to complete this computation, to make it something somewhat cogent, is that we need to be able to move the adjoint of this control Liouville operator onto this control occupation kernel. And so, of course, this is a densely defined operator, and so we need to verify that this control occupation kernel is going to be in the domain. And I should also mention that we are assuming that these occupation kernels are inside the domain of the original control Liouville operator. So, how do we verify that the control occupation kernel is actually inside the domain? Well, that's not too bad. So what we need to do is we need to show that AFG acting on H, where H is from our scalar valued reproduced kernel Hilbert space, this quantity interproducted with our control occupation kernel, where we have a control trajectory, gamma sub mu, and our controller, U, that all correspond to this control affine system. Well, if I go ahead and act on H, then I know I'm going to get the gradient of H times this matrix Fg. And when I take the inner product against this control occupation kernel, well, we're going to be taking a look at the integral from 0 to t of this gradient of H times F and G, and all of these are going to be evaluated at our control trajectory evaluated at t. Now, this quantity is going to be multiplied by the column vector 1 and u of t, and this whole thing is integrated dt. Now, if I go ahead and multiply out the matrix with that column vector, ultimately what I end up getting is I get f at the control trajectory evaluated at t plus g at the control trajectory evaluated at t times u of t. And well, this is simply the derivative of our controlled trajectory. And so then that means that we're taking the integral of the gradient of h evaluated at our controlled trajectory times the derivative of the controlled trajectory, which itself is the time derivative of h composed with the controlled trajectory. So that means we can use a fundamental theorem of calculus in order to integrate, and so we get h evaluated at the two endpoints of this controlled trajectory. And this finally can be rewritten as h interproducted with the two kernel functions centered at the endpoints of our trajectory. So that tells us that our controlled occupation kernel is actually in the domain of the adjoint of the Liouville operator. And more than that, it tells us that if we want to compute these entries in this column, then that really just boils down to evaluating the occupation kernel and taking the difference at the two endpoints of each one of these control trajectories all the way down. So that gives us the projection of the image of our first occupation kernel onto the span of these control occupation kernels. And then we just need to fill it out with all the other ones, and then ta-da, we have now a finite rank representation for this control Liouville operator. But we're not done yet. Control Liouville operators don't actually have any dynamics in them because we are removing the dynamics with these control occupation kernels. And so there is no dynamic mode decomposition working directly with these, and we need to be able to get some dynamics out of it. And that's what this multiplication operator does. And now the multiplication operator itself is going to now take these functions from our vector valued space, which are now all going to be expressed as a linear combination of these control occupation kernels, and we're going to go ahead and map that back to a scalar valued reproducible kernel Hilbert space. And then finally, we're going to project back down onto our regular occupation kernels. Now let's take a look at the multiplication operator. Now again, we're going to make the assumption that our control occupation kernels are actually inside the domain of our multiplication operator. And so what we're going to do is going to take each one of our control occupation kernels, and we're going to look at its image underneath this multiplication operator, and then we're going to take that image and we're going to project it onto the span of our occupation kernels. So in order to compute this projection, well, we again need a gram matrix of our occupation kernels, and we've made that before. And so here it is. Now we're going to take the inverse of this gram matrix, and we're going to hit it against a vector that corresponds to the image of our control occupation kernel underneath this multiplication operator. And we are going to take the inner product against each one of the occupation kernels corresponding to the control trajectory. So what we have to do now is we want to be able to, say, move that multiplication operator as an adjoint onto the other side and impact our occupation kernel. But again, we need to demonstrate that this occupation kernel is going to be inside the domain of our multiplication operator's adjoint. And so, in order to do that, what we're going to do is we're going to take a look at the generic equation where we're looking at P mapping to the multiplication operator acting on P interproducted with our occupation kernel corresponding to our control trajectory. If we verify that this is a bounded functional, then that means that the occupation kernel corresponding to our control trajectory is inside the adjoint of our multiplication operator. That's what it means. So why don't we go ahead and work out exactly what this ends up being. If I take a look at the multiplication operator acting on P, then what this is going to end up giving me is P times 1 and mu. Then if we take the inner product of that quantity against our occupation kernel corresponding to our control trajectory, what we end up getting is we have the integral from 0 to t of p evaluated at our control trajectory at t times the column vector 1 and mu, where mu is also evaluated at our control trajectory. Now, this is integrated dt, and this is exactly p interproducted against our control occupation kernel corresponding to the control trajectory, and this different quantity, not the true controller for that control trajectory, but rather mu composed with the control trajectory. And that becomes our new controller for this new control occupation kernel. If you then take a look back at the projection equation, we now have the control occupation kernel corresponding to a particular controller that we did observe. And down this column, we are taking a look at the inner product against new control occupation kernels, where each one of these has a different controller that is expressed as mu composed with each one of the control trajectories. And so what this inner product is doing is it is basically taking a comparison between the controllers that we observed and what would have happened if we tried to use this mu as a controller for these different control trajectories. And so the more similar they are, then the more they line up and they'll have a larger value, and the more orthogonal these are, different they are, in a sense, they're closer to 0, closer to orthogonal they're going to be. In any case, so that gives us the projection of the image of our first control occupation kernel underneath the multiplication operator, and this is projected onto our occupation kernels corresponding to the control trajectories. And so then we do this one at a time until we have computed all of the columns, and each one of these columns corresponds to our control occupation kernels. So we are finally at a point where we're done. We have a finite rank representation of our control Liouville operator that takes us from a scalar valued space to a vector valued space. And then we have this multiplication operator that takes us from this vector valued reproduced kernel Hilbert space back to a scalar valued reproduced kernel Hilbert space. And this overall finite rank representation that you get when you combine the two of these together ends up being a finite rank representation of the Liouville operator that corresponds to the dynamics that themselves correspond to the state feedback controller that we were wondering about. Okay, so here's a roadmap to making the finite rank approximation. And so what we do is we start with the finite dimensional space spanned by our original occupation kernels. Then we are hitting those with the control Liouville operator. Then after we hit it with control Liouville operator, we're going to be in a vector valued space. And so then in this vector valued space, we project down onto the control occupation kernels. Then we take these control occupation kernels and we are hitting these with the multiplication operator. The multiplication operator is going to take us from the space of vector valued functions, and it is going to map us back to the space of scalar value functions. And then finally what we do is we project down onto the occupation kernels that we started with on the other side. And so throughout this entire thing, this is basically giving us a finite rank representation of the Liouville operator that corresponds to the closed loop dynamical system that we get when we use the state feedback controller mu that we have in hand. So now the objective is to do a spectral decomposition of this finite rank representation, and then to find eigenfunctions. And once we find these eigenfunctions, to project the full state observable onto these eigenfunctions. And once we do that, we can use the eigenfunction property for regular Liouville operators that basically says that if we take a trajectory from our dynamical system corresponding to the dynamics inside that Liouville operator, then ultimately what ends up happening is that these eigenfunctions evaluated along this system state just becomes e to the lambda t times the eigenfunction at the initial point. And so then we can use this property to change this projection of the full state observable, and we put the x of t inside the full state observable, and then on the other side we just get a sum of exponentials. And this is our approximation of our system state, or rather it is our model of the system state that corresponds to the closed loop dynamical system obtained from the state feedback controller. And so the computations that go into this last part are exactly like what we saw before for continuous time dynamic mode decompositions with Liouville operators and occupation kernels. So this bit I'll leave to this other video, and you can go and follow from that point on, and that basically tells you how to do this construction.
Okay, so that was dynamic mode decomposition for control affine systems. And we introduced a new kind of multiplication operator, vector valued reproducing kernel Hilbert spaces, and we also talked about control Liouville operators and control occupation kernels. So there's a lot to process in there. And I hope I did a decent job on keeping things coherent. And, well, yeah. Anyway, so if you want to see more of these cool techniques for data-driven methods for dynamical systems, please subscribe and come back. And until I see you next time, well, have a good day. Oh, hey, buddy. Oh, okay. All right. Got some lawnmowers coming.